Hello, chemistry students. Professor Sean McMahon here with our third lecture of chapter 4. And in the last two lectures, we were really focusing on the subatomic particles, the protons as far as their atomic mass unit. Neutrons have an atomic mass unit of 1 as well. How we were able to identify an element based on its elemental symbol. Also using the atomic number to find it on the periodic table, the atomic number being the number of protons, and then using the average atomic mass. In the case of isotopes, we would look at just the mass number to determine the number of neutrons for that particular isotope, that atom of that isotope. But we realize on the periodic table, the average atomic mass is not a perfect integer because we did calculations to show that it is a weighted average of the masses of the isotopes for that element. So in this lecture, what we're going to do, now that we've kind of understand the law explaining what is happening, we're going to go more into why. Why are these elements having similar physical and chemical properties? Why are we able to stack the elements into these vertical columns or groups and families? Why do they have similar characteristics? And again, the last couple of lectures, we were really focusing on, again, the atomic number, the number of protons, the mass number, the number of protons and neutrons, and how to calculate the average atomic mass based on the frequency of the isotopes. In this one, we're going to focus on the physical and chemical properties, and that all boils down to the electrons. So chemistry is all about the electrons. Therefore, how the electrons are organized in the atom is a very important concept. So far we were just looking at it in terms of the nuclear atom, where we have this dense nucleus where the protons and neutrons are, and that's pretty much the mass, okay? And then outside are these electrons that are negatively charged, okay? But their mass is negligible. But what we're going to find out is it's this exchanging of electrons that groups the atoms together and provides certain characteristics. So we'll see that the reactivity and the arrangement of the periodic table are related to the electrons. But to be honest, that focus will be the electron arrangement discussion for chapter 4, which is kind of the 4th lecture. This is a little mini lecture that I'm sneaking in for this particular class. Your book does not go into a huge discussion on light. I feel like I need to add this discussion because it all started with light. We learned about electrons by studying light, okay, and how it interacted with atoms. So I can't skip this section. I have to insert it. It won't be a long lecture, but I'm adding this section, okay? So light is a form, okay, of electromagnetic radiation. It's not really matter, it's energy. And remember, in chapter 3, we were looking at matter and energy, okay? So energy is, something that can do work. And when we talk about electromagnetic radiation, right, it travels at a certain speed. And that speed is the speed of light. You may have heard this. You may have even seen it in an equation that's pretty famous. Energy equals mass times the speed of light squared. So if we get a really small subatomic particle, like an electron, traveling at the speed of light, it's going to have energy, okay? But basically, electromagnetic radiation also has this energy, and it's traveling at 3.0 times 10 to the minus 8 meters per second. So I always like to kind of bring this up is, how fast is that, okay? So one of the things that I like to compare is the speed of sound versus the speed of light. We broke Mach, 1, the sound barrier. We can fly faster than that in actuality. But how can we relate it? Well, one of the things is you think of thunderstorms, right? When you see lightning, you see that first, And then there's where you kind of count, the number of seconds until you hear the thunder, and that kind of tells you the distance. Well, that's because the light travels so much faster than the actual sound. Okay. Well, how much? As I said, the speed of light, which is denoted with the c. And in this course, we don't do calculations, and a lot of other courses you do. Okay. But the speed of light is 3 times 10 to the 8 meters per second. The speed of sound is 340 meters per second, but I'm going to put it in scientific notation, and that is 3.4 times 10 squared meters per second. Now, how big of a difference? Well, 10 to the 8th, right, compared to 10 squared, right? If we subtract the exponent, is 10 to the 6th. All right, 6 zeros, that's 1,000,000 times faster. So light is 1,000,000 times faster than sound. I just thought that was, I wanted to throw that in just to give you a relative idea of how fast electromagnetic radiation actually travels. So when we talk about light, we need to think of waves. Now, this is kind of a crude model. It's actually a sinusoidal wave, where the reason why it's called electromagnetic radiation, there's an electric field, and then there's a perpendicular magnetic field. We're going to make it very simplistic and just look at it in terms of just similar to a trigonometric function, a wave like this. Okay. So when we're looking at waves, we want to look at wavelength and frequency. So wavelength is using the symbol lambda. Okay. But it's really easy to identify wavelength because it's typically peak to peak. And you could measure it from trough to trough, or they sometimes refer to as node to node, but the most common is peak to peak. You can think of it like the crest in the waves at the beach. Okay, so it is a length, and typically in the standard international system of units, that would be meters. Okay, now frequency is a little bit different. Okay, the way frequency works is if I take a point in space, all right, and that actually is not a V, it's like a little nu. There should be a little tail on that V, that symbol. But the way frequency works is it was really common with records back with revolutions per minute, but you can think of it as a per second. So what do I mean by a per second? If I pick a point in space, how many of these peaks are going to pass that point in space in 1 second? Right? So you have your wavelength, it's traveling at the speed of light. So no matter what, you're going to have a certain number of peaks pass a point in a second. And that number of peaks per second is what we call frequency. Now, there is another component of light, and that's amplitude. Okay, so typically what happens is if the amplitude is higher, you have a brighter light. Okay, if the amplitude is shorter, you have a dim light. And you may have heard of, AM radio. I know it's old school. Amplitude modulated, so you can modulate the amplitude of the radio wave. But essentially, the amplitude changes the brightness. It doesn't change the color. So the color is related to the wavelength. Okay, so we see here for this particular wavelength, a longer wavelength, we see red light. For a little bit of a shorter wavelength, we're seeing yellow. And if it gets even shorter, we see blue. So the shorter the wavelength, the more it goes blue. The longer, the more it goes red. So wavelength determines the color. Now, going back to frequency, if I have a longer wavelength, I will have a shorter frequency. So what does that mean? Well, hertz is interchangeable with per second. Okay, and you can even see that this point in space, it's saying right here per second. If in 1 second I have 2 peaks pass, that frequency is 2 hertz, so 2 peaks per second. If I have a shorter wavelength, but now that light is traveling at the same speed as the longer wavelength, because they're traveling at the speed of light, I'm going to have a higher frequency. Why? I'm going to have more peaks, because this whole thing is going to shift in a second. I'm going to have more peaks past that point in a second. So it'll have a higher frequency. So what we're noticing is that when wavelength is reduced, the frequency goes up. So what does that mean? They are inversely proportional. Now remember, I said the speed of light, c, is roughly 3 times 10 to the 8 meters per second. Remember, lambda, your wavelength, is meters, and nu, your frequency, I know it says hertz here, but it's per second. So the number of wavelengths in meters traveling per second through a point of space is based on, the speed, right? So if the wavelength, right, if these two things have to be a constant value, if wavelength goes down, then frequency has to go up. So they are inversely proportional, right? So with a longer wavelength, less peaks pass, I have a lower frequency. That's because I have a longer wavelength. With a shorter wavelength, more peaks pass, so I have a higher frequency. So what does that mean? If I decrease wavelength, frequency goes up. They're inversely proportional, okay? Now, why am I even bringing this up? Well, in the early 20th century, we're using light to essentially knock off electrons from atoms to learn about their behavior. So scientists like Einstein saw that light was actually not a classical wave, like how we think, like in a string. So they explained that light actually behaves like a particle, which we call photons. And right now, if you're anywhere, you're being bombarded by photons because light is coming in. Essentially, when we say light, light is a form of electromagnetic radiation, waves, okay? But even though earlier we said it does not have mass, they behave as particles. That's referred to as wave-particle duality. It's a little bit beyond this class, but I still want to talk about light because it helps us. So one of the things that we know with light is we can separate it. So we can shine light through a slit, through a prism, and it'll bend it, okay? So the longer wavelengths, like the red light, because they're longer wavelengths, when they go through the prism and the little crevices in the prism, they don't bend as much because they can go around the little crevices. When we have, oops, I'm sorry about that. When we have shorter wavelengths, like violets, right? Their wavelengths are much smaller, so the crevices actually can bend that light much more. And what we end up getting is we spread the white light into its components, okay? So visible light, if I bend it through a prism, gives me a rainbow, right? And what we notice is that the higher frequency, right, the shorter wavelengths bend the most. But with light, white light, visible light is really what we should be saying, we get a spectrum of individual colors when we bend it. And we see this every day with a rainbow, right? So when there's a lot of moisture in the air and the sun comes out, well, that moisture is, bending the light of the sun into rainbows. And the way you can remember the spectrum of visible light is the acronym Roy G. Biv for red, orange, yellow, green, blue, indigo, and lastly, violet. Violet being the shortest wavelength, red being the longest. So when we look at the electromagnetic spectrum, visible light is a very small portion of all light. So here's visible light in the full spectrum of light, electromagnetic radiation. And if I was to take this small region, if you look, it's based on frequency or wavelength in nanometers. The reason why they choose nanometers is because when we look at visible light, it brings it to a magnitude that we can relate to. But remember, nanometer is much smaller than a meter. So I need 10 to the 9 nanometers, basically a billion nanometers to make 1 meter, okay? If I take this small region of space on this spectrum of light and I kind of expand it to make it easier for us to read, what we see is the longer wavelength for red visible light is 700 to 750 nanometers. And the shortest wavelengths, right, the violet, is 400 nanometers. Now, why is this important to understand that visible light is only a small portion of all light? Because we can't see all forms of energy that travel through electromagnetic radiation. We just don't, okay? So why is that? Well, the way the light comes in through our iris, it has to be a certain size so that it can go through the iris and hit the back of our retina and cause a stimulation to induce a neurological impulse so that we see color, all right? But there are forms of electromagnetic radiation that are longer, and there are forms that are shorter that we can't see. So an example, if I look, and this Roy G. Biv is backwards, but that's okay. Sorry. Right? If I look, red's the longest. What's a little bit outside of the visible spectrum, right? And it's a little bit longer, infrared. So infrared is typically associated with heat. And, you know, it's kind of funny, if you've ever gone on a long road trip and you're looking down, maybe you're driving and you're looking down the highway, you see off the asphalt the little heat waves. And you can sometimes even see shadows of it, or, you know, people call it, if you're like really thirsty, you're hallucinating, but really you're seeing infrared, kind of, not exactly, but so that's basically what you're seeing. So infrared is a little bit longer, and its amount of energy, it's associated with heat energy. Now microwaves, what do we use microwaves for? To heat up food. Why? Microwaves come in at a longer wavelength. So when you put food in a microwave, the wavelength comes in, goes through the food, and it's large enough where the molecules in the food now begin to vibrate and agitate and move and heat up your food. So a microwave, typically microwaves are like in centimeters, the wavelengths, okay? So those are much bigger. So when they come in and hit the food, they're causing vibrational energies, and that heats up your food because it's moving it, right? More kinetic energy. If we go even further and get really, really long wavelengths, now we're talking TV and radio waves. Radio waves are so long, they go around us, right? They're not going in our eye or through us, right? They're going around us. They're so big, in fact, they go around buildings and they travel great distances. The only time they kind of get some interference is if you have like a range of mountains. That's why when you drop down in valleys, you sometimes have to tune your radio because the radio waves are getting blocked. And earlier I talked about amplitude influencing the brightness of light, for example. Well, AM radio is amplitude modulated. Well, what's FM? Frequency modulated, and modulates the frequency. So this assists how the radio waves travel through space, because when they travel, they're a form of energy which is actually delivering information. Okay, that energy is giving us information. Now, if I go to the other side of the spectrum, so these are all longer wavelengths. which means they have shorter or smaller frequencies, right? Because a longer wave means less peaks per second. If I go to the other side where I have shorter wavelengths, I'm going to have higher frequencies, okay? So what would be shorter than violet? Ultraviolet, right? So you hear how the sun has ultraviolet light that causes skin cancer. Well, why is it? Now it's small enough where it gets into the epidermis skin cells and it causes mutations in the DNA molecule by breaking bonds. And now it doesn't code for the information correctly, and then it doesn't communicate, and then you end up resulting in no control of growth and melanomas. Well, what's even smaller than UV? X-rays. Well, how small are X-rays? Well, essentially what an X-ray is whatever's in the dark, that's the X-ray going through your body and touching the film and basically it's like going through and hitting the film and turning it black. What it doesn't go through is hard tissue, like your bones. So when when you go to the doctor, you put on the lead apron to protect your vital organs. That's because they don't want the X-rays getting stuck in there, right? So when they take an X-ray of a broken bone, it's going through the soft tissue, but it gets stuck in the hard tissue. Small doses are fine as long as it's bone and not vital organs. And then what's even smaller? Gamma. Gamma goes right through everything, but gamma's bad. Okay, just think, the Hulk. So I hope that helps you kind of understand all forms of electromagnetic radiation, kind of where the visible light that we see falls. It's only a small region, but by no means is it the only form of light. In fact, the majority of light is outside of the visible region, yet it's everywhere. So you're getting this electromagnetic radiation. It's how energy travels through the universe. So why am I bringing up? It was the study of light that introduced the concept for the Bohr model and how the atomic spectra. So when atoms or molecules absorb energy, okay, that energy a lot of times is released as light. So fireworks, neon lights, okay? So here are some example of gas discharge tubes. Basically, each of these tubes has a different element. So when you put a voltage or a current through it, right, you have the atoms in a gaseous form, right, around the nucleus or the electrons, and they get, when you put energy in the form of electric energy, the electrons get excited. But they're still attracted to the nucleus. But what goes up, just like if I throw a ball up, what goes up must come down. So what happens is they absorb the electrical energy, it's an absorption, and when they drop down, it's called relaxing. When they drop down to where they belong, it releases that energy, it absorbs, it's called an emission, and you see light. So typically, with a lot of reactions, there's a release of light. An example, combustion. When I burn things, not only is there a change in the molecules, because I'm breaking bonds, rearranging atoms, forming new ones, it's accompanied with changes in energy in the form of heat and light. So you actually see this with flame tests. You can burn different elements, and based on their electronic structure around the nucleus and where the electrons are located in that atom, when you burn it, right, it excites. And because there's a different, distance of the electrons getting excited and dropping down, they release different colors. And it's a way to identify elements. It's actually really fun. It's really common lab. So the unique thing is we learned from light that, okay, unlike white light, which is a continuous spectrum of all the different energies, elements, when they absorb energy and release light, and we put it through a prism and a slit, we get distinct lines. And those distinct lines are called atomic emission spectrum. and they're essentially a fingerprint. So every element has a different emission spectrum. And that's because every element has a different number of electrons, and those electrons are located in different places. Okay. But what I want to emphasize is it is not a continuous spectrum. There's not all levels of energy. There's different levels of energy, and that's why we only get a few lines. Now, obviously, when the elements have more electrons, so hydrogen, if you look on the periodic table, it has the atomic number 1, it has 1 electron. Helium, it's 2. So it has 2 electrons, a little more complicated. When we go to neon, its atomic number is 10, so it has 10 electrons, it gets more complicated. But it's not a continuous spectrum. So the reason why I wanted to bring this up is it was our study of light being absorbed and released that helped us understand this atomic emission spectra, and then how to understand the electron arrangement in atoms to help us understand why certain elements have certain physical and chemical properties and reactions. So we'll continue with the atomic line spectra and focus on the electron arrangement in the next lecture, now that I'm done with light. And I want to thank you. I know this is not in your current book. It's additional information, but I felt it was necessary to help you understand. So I want to thank you guys for your patience. And that is kind of the third lecture of chapter 4, but I'll organize it a little bit different. So thank you so much, and I'll see you in the next lecture.